Okay, so now what do we want to do with this information? How powerful, just how powerful is Newton's law of universal gravitation? Well, there's a couple things that you're going to be responsible for understanding and knowing what to do on the AP exam. And the first of that is looking at using Newton's law and basically setting up proportions to figure out relative information about other planets. So this formula right here doesn't necessarily need to be two objects that are separated in space by a distance, but we could actually use that to determine the weight of an object on top of any planet. So that radius, and that should be radius squared, not r sub 2. So if I am a person just standing on the edge of the planet, then that radius would just be the distance from the center of the planet to the surface of the Earth. So we can use that information to travel to other planets. So here we go. We're traveling to other planets. So let's say we're on this planet here, and we're at mass m2, and then the mass of the planet is big M, and the planet has a radius of r. My weight, or the force of gravity of a person standing on the surface of that planet, would just be Fg. And if I know the information about the planet, I can just calculate it this way. Now let's say we get on a rocket ship and we go to another planet that has the same diameter, same radius, but now it has 3 times the mass. Well, if we use Newton's law of gravitation, my mass stays the same, but now I'm tripling the mass of the planet. That in effect is going to triple the force of gravity that I would feel on that planet. So I would feel 3 times heavier on that planet. So that's one thing where you mess with the mass of the planet. Okay? We can also mess with the diameter of the planet. So again, I'm on the planet's surface. I have a force of gravity that I can calculate using Newton's law of universal gravitation. Now I go to another planet that has a greater diameter but the same mass. So I've in fact have doubled the radius. Well, affecting the radius is going to use that inverse square law. So whatever I do to the radius, I take the inverse of it and I square it. So inverse of 2 is 1/2. I square it, 1/4. That means my force of gravity is going to be 1/4 as much as it was on the original planet. So I would feel 4 times lighter. So just playing with some of these ratios is something that we're going to do on the worksheet that's coming up. All right, the second application of Newton's law is calculating g for any planet. So g is that acceleration due to gravity, which is measured in meters per second squared, or we also call it the gravitational field strength and measured in newtons per kilogram. So more so than ever, we really need to be familiar with the vocabulary and what it all means. So in the past, our equation for the force of gravity was very simple. It was just m times g. So if I was on a planet and I had some object, m1, that was lifted above the surface and I released it, well, there would be a net force acting on it, and it would be the weight of the object pulling it towards the planet, and we'll make the planet big M. That acceleration that it would feel would be that 9.8 meters per second squared that we were feeling, and its weight would just be the mass times our gravitational field strength. But now we have some more information about how to actually calculate g, and it depends on how far away you are from the center of the planet. So g, although we treat it as a constant, actually does vary with its radial separation from the other object. So from Newton's law, this force of gravity is also equal to big M times little m over r squared. So these m's cancel out, and we get a formula for g times big M r squared, where m is going to be the planet, and again r is going to be the distance between center of mass to center of mass. So the same kind of ratioing that we could do for the force of gravity when we travel to different planets, we could also do the same thing with how the gravitational field strength, or the acceleration due to gravity, changes with altitude. So we can use this equation to calculate g on any planet. Okay, the third thing that we can do is we can determine the mass of any planet. And this is why, if we bring back our equation that we just derived, g is equal to big G, mass of the planet times the radius squared. I'm going to solve this for the mass of the planet, so just rearranging the equation, I get g r squared over big G. When Cavendish did his experiment, and he was able to determine this value of g to 6.67 times 10 to the minus 11th, They knew the acceleration due to gravity on the planet Earth because it's already been established with experiments and just measuring distance and time and all that kind of thing. The radius of the Earth was also known, and they figured that out by looking at shadows and eclipses and different times of the year, so they were able to determine the radius of the Earth. So once Cavendish was able to determine g, they were able to figure out what the mass of the Earth was, and that's why his paper where he published the value of g was actually called Weighing the Planet. So that's the mass of any planet. We can use this equation. Again, all these equations, except for Newton's law of universal gravitation, are not given to you. You need to be able to derive them or see them inside the equations. Now, the money. The money question is what Newton was after all along, and this was being able to describe satellite motion. So if we look at an object here, a satellite that is in orbit has sufficient horizontal speed so that it perpetually just falls around the planet. And if you recall that Newton's cannon was a thought experiment that Newton had gone through to really kind of postulate what an orbit was and why the moon orbits around the Earth. So if we look at just a circular orbit, which is what we're going to assume for the problem solving in this level, as it moves around the circle, the only force acting on it, again, is going to be that force of gravity, and that is going to act as our centripetal force. So once again, we have the sum of the forces is equal to m times a. So now we're combining two of Newton's laws. This centripetal force is just going to be the force of gravity, and that's going to be equal to mass times my centripetal acceleration. That force of gravity is going to be equal to mv squared over r, which is going to equal g, we'll call it little m times big M, over the radius squared. Now, be mindful that this little m right here, that is the mass of the satellite. That's the thing going around in the circle. This is the planet. And it's important to understand which m is which. So I can cancel these out, and I can derive a formula. One of these radius cancels with one of those. For the orbital speed or satellite speed is g times m times r. And this is a formula for satellite speed. Again, we're assuming a circular orbit and constant speed. So again, this formula right here is not given on the equation sheet. It actually gets derived, and it's an important thing to remember. We also know that this formula also still equals 2 pi r over t. So if we know how much time it takes to do one revolution, this is another useful formula that we'll use in circular motion. So just summing up some of the stuff that we've done so far, we know that our force of gravity is equal to mg, and it's also equal to g big M times little m times the radius squared. So that's something that we've known what the force of gravity is. We just have a little bit more detail on what this gravitational field strength is. The gravitational field strength is going to be universal gravitation constant times the mass of the planet. Again, big M is going to represent the planet or whatever is at the center, the central body, because it could be the sun or anything else. And we also know for objects that are in circular motion, so now if we look at an orbit, this is also equal to our centripetal acceleration, which is equal to v squared over r. And we know that we have derived v to be equal to g times big M, mass of the planet, over r squared, over r, square root of that. And we also know that this is equal to 2 pi r over t. So these are important relationships to understand. This is given on the exam. This is conceptual connections that you need to make. So with all these kind of sets of equations, I guess you get that one too, you can go through the problem solving. Again, the biggest trip up is really making sure that you understand what the masses are, what they represent, and what that radius means. So in Newton's laws, g big M little m over r squared, and then you have this is our centripetal acceleration. This r represents the center of mass to center of mass distance. Remember, and this radius represents the radius of the circle. So we just want to be mindful. Sometimes they're the same number, but we'll find out that sometimes they are not. So hopefully this is helpful just as a quick summary of the lecture that we did in class.